Okay, so now we're going to be discussing about solving a couple of first order linear differential equations. So first we have this problem. So we write it down. We have x dy dx plus x squared y equals x. First thing we must do is we check that it's even in the form. The answer is no, because it's not in the form dy dx plus p of x y equals to q of x. To make it into the form, we divide by x to both sides. We have dy dx plus, well, x squared divided by x just becomes x, y equals to 1. Now, it is in the form. 2. We identify what p of x is. P of x in this case is equal to x. 3. We integrate this, we find our integration factor, which is equal to I equals to the exponential of the integral of p of x, which in this case is x, dx. In this case, we get exponential of 1/2 x squared. Now, in this situation, this is considered an intermediate calculation. As such, we don't include a plus c into here. Now, 4. What we end up having is the following. We have ddx, and we should be okay just writing this nominally. So we just have y e to the x squared divided by 2, multiplied to the other side as well. Now, unfortunately, looking at this part, the right-hand side has no simplified result. So as such, we're actually going to keep it as it is. So we have y e to the x squared divided by 2 when we integrate both sides equal to some integral of x squared divided by 2 dx plus c. Of course, it doesn't make any sense in this situation to include the constant when we didn't integrate it, but suppose that this was our answer 1, and we have then answer 1 plus c, or times e to the x squared divided by 2. Sorry, let me write that better. X squared divided by 2. Now, 6, divide this to both sides, giving us y is equal to some kind of answer 1 divided by e to the x squared divided by 2. Here in this situation, we can actually simplify now that we know what I is. So it's going to be negative x squared divided by 2. And that's going to be our result. So the tricky part about first order linear differential equations is that on occasion, you will pass by what are termed non-elementary integrals, which are just simply integrals that have no definitive result. So as such, we usually keep it in the integral form. And that is our result for the first problem. Now, the second problem, we check. So it's going to be dy dx plus e to the xy equals x. Now, as we have done with the first problem, we check, is it in the form? The answer is yes. 2. Now we have to identify what our p of x is. P of x is equal to e to the x. 3, we find our integration factor, which is equal to the exponential of the integral of e to the x dx. Now, this might appear as a weird form, because it is. So we have e to the x, a kind of nested Euler. Then we have over here number 4, which we will simplify down to the following. Y e to the x equals to x e to the x. We integrate both sides, or rather, in theory, we could integrate both sides to get us the following. E to the x dx plus c. As discussed with the first problem, sometimes it doesn't necessarily make a lot of sense to keep it like this, but this one, just like the result, is undefined, or rather, not undefined, but does not have a simplified representation. So as such, we have to keep it like this. 6, divide e to the x to both sides. We get y equals to answer 1 divided by e to the x plus c e to the negative e to the x. And that would be our result. Now, these two problems are not merely to demonstrate that this first order linear differential equation is unsolvable. Merely this was a coincidence. In general, though, we can use first order linear differential equations, or the method to solve them, to solve for RL or RC networks. So let me give you a specific example where we could actually solve the first order linear differential equation. Suppose you're given an independent source, and let's say it's modeled by V. We have a resistor, R, and we have a capacitor, C. Now, we assign some polarity based on this current direction. By Kirchhoff's voltage law, we have that V is rise, drop, drop is equal to, so in order to obtain a voltage term, it's going to be Ri plus, the voltage for this is 1 over C Q. Now, in this situation, we have to find what the charge is. So assuming V is a constant, we have that I is the instantaneous change of the charge divided by time, or over time. So as such, we have R dq dt plus 1 over CQ equals to V. Now, if you notice, this looks like a kind of first order linear DE form, but we have to do a few things first. One, we have to divide R to both sides. We get 1 over RC Q equals to V over R. In this case, V over R is just current, which matches with this situation here. Now, our integrating factor, or our pseudo P of x, is 1 over RC. And as such, we can find the integrating factor given as such. 1 over RC t. This right here is just e to the t divided by RC. We can simplify this, giving us ddt of q e to the t divided by RC equals to V over R e to the t over RC. Integrate both sides. We get q e to the t divided by RC equals to, in this situation, it's going to be divided by RC, so it's actually multiplied. R times C e to the t divided by RC plus C. Or rather, let's say plus a constant. Now, so as such, Q is equal to, Q of t is equal to some Q naught e to the, so our result here is C times V, and then once we divide here, we just get this plus QE to the negative T over RC. And actually, what ends up happening is that we can actually show with our given initial conditions that this actually models this following network. 1 minus e to the negative t divided by RC times Q naught. And this right here, alongside the voltage relation as well as the current relation, gives us the behavior of a first order circuit system. So that is one specific example where this is plausible and useful. But the first two were just to show that sometimes it's not doable. Okay, thank you.